In complexity theory, the class APX is the set of NP optimization problems that allow polynomial time approximation algorithms with approximation ratio bounded by a constant. In simple terms, problems in this class have efficient algorithms that can find an answer within some fixed multiplicative factor of the optimal answer. An approximation algorithm is called an approximation algorithm for input size if it can be proven that the solution that the algorithm finds is at most a multiplicative factor of times worse than the optimal solution. Here is called the approximation ratio. Problems in APX are those with algorithms for which the approximation ratio is a constant. The approximation ratio is conventionally stated greater than 1. In the case of minimization problems, is the found solution's score divided by the optimum solution's score, while for maximization problems the reverse is the case. For maximization problems, where an inferior solution has a smaller score, is sometimes stated as less than 1. In such cases, the reciprocal of is the ratio of the score of the found solution to the score of the optimum solution. If there is a polynomial time algorithm to solve a problem to within every multiplicative factor of the optimum other than 1, then the problem is said to have a polynomial time approximation scheme. Unless P equals NP, there exist problems that are in APX but without a PTAS, so the class of problems with a PTAS is strictly contained in APX. One such problem is the bin packing problem. APX hardness and APX completeness. A problem is said to be APX hard if there is a PTAS reduction from every problem in APX to that problem, and to be APX complete if the problem is APX hard and also in APX. As a consequence of PNP PTAS APX, PNP implies no APX hard problem has a PTAS. In practice, reducing one problem to another to demonstrate APX completeness is often done using other reduction schemes, such as L reductions, which imply PTAS reductions. Examples: one of the simplest APX complete problems is MAX3 SAT3, a variation of the Boolean satisfiability problem. In this problem, we have a Boolean formula in conjunctive normal form where each variable appears at most 3 times, and we wish to know the maximum number of clauses that can be simultaneously satisfied by a single assignment of true, false values to the variables. Other APX complete problems include max-independent set in bounded degree graphs, min-vertex cover. The complement of any maximal independent set must be a vertex cover. Min-dominating set in bounded degree graphs. The traveling salesman problem when the distances in the graph satisfy the conditions of a metric. TSP is NPO complete in the general case. The token reconfiguration problem, via L reduction from set cover. Related complexity classes. PTAS consists of problems that can be approximated to within any constant factor besides 1 in time that is polynomial given that constant factor. This class is a subset of APX. APX intermediate. Unless P equals NP, there exist problems in APX that are neither in PTAS nor APX complete. Such problems can be thought of as having a hardness between PTAS problems and APX complete problems, and may be called APX intermediate. The bin packing problem is thought to be APX intermediate. Despite not having a known PTAS, the bin packing problem has several asymptotic PTAS algorithms, which behave like a PTAS when the optimum solution is large, so intuitively it may be easier than problems that are APX hard. One other example of a potentially APX intermediate problem is min-edge coloring. FAPX1 can also define a family of complexity classes APX. Where APX contains problems with a polynomial time approximation algorithm with her approximation ratio, one can analogously define APX complete classes. Some such classes contain well-known optimization problems. Log APX completeness and poly APX completeness are defined in terms of app reductions rather than PTAS reductions. This is because PTAS reductions are not strong enough to preserve membership in log APX and poly APX, even though they suffice for APX. Log APX complete, consisting of the hardest problems that can be approximated efficiently to within a factor logarithmic in the input size, includes min-dominating set when degree is unbounded. Poly APX complete, consisting of the hardest problems that can be approximated efficiently to within a factor polynomial in the input size, includes max independent set in the general case. There also exist problems that are exp-APX complete, where the approximation ratio is exponential in the input size. This may occur when the approximation is dependent on the value of numbers within the problem instance. These numbers may be expressed in space, logarithmic in their value, hence the exponential factor.